If we are going to have a truly honest discussion about the state of the automotive industry in 2026, we need to start by exposing a myth that has survived for more than 140 years. Ever since the first internal combustion cars rolled out of small workshops in Germany, the basic connection between the vehicle and the road has remained shockingly primitive. Luxury brands like Mercedes-Benz, Bentley, and Rolls-Royce have convinced us that suspension technology has evolved dramatically. They promote seductive phrases like magic body control or active ride. But strip away the leather interiors, polished wood, and thick sound insulation, and the mechanical reality is far less impressive. Underneath all that luxury is a system that hasn't fundamentally changed since the days of Victorian horse-drawn carriages. Modern cars still rely on a passive setup, a steel spring that carries the vehicle's weight, and a hydraulic damper filled with oil to stop that spring from bouncing endlessly. And this design is built on compromise. It works on a simple rule: reaction. The wheel first has to hit a bump in the road. It gets pushed upward violently. Only after that impact does the damper try to control the movement by forcing hydraulic fluid through extremely small valves. This delay creates a well-known physics problem called hysteresis. Even if the computer inside a modern Porsche Panamera reacts instantly, the oil inside the shock absorber still has viscosity. Fluids take time to move. Pressure takes time to build. So there will always be a delay between the moment a bump happens and the moment the suspension reacts. For more than a century, engineers convinced us that this delay was unavoidable. They told us that comfort and performance could never exist together, that a car could either ride smoothly or handle sharply, but never both. They claimed it was simply the law of physics, but that was never entirely true. The solution actually appeared decades ago. To understand it, we have to go back to the early 1990s. The legendary Williams F1 team built the revolutionary Williams FW14B. This Formula One car used fully active hydraulic suspension. The system controlled ride height in real time and delivered such overwhelming performance advantages that the Fédération Internationale de l'Automobile eventually banned it. At the same time, a brilliant engineer named Amar Bose was working on something even more radical. For over 30 years, the founder of Bose Corporation invested hundreds of millions of dollars into developing electromagnetic suspension. His experimental Lexus prototypes could literally jump over obstacles and corner without any body roll. But the automotive industry rejected the technology. Manufacturers claimed it was too heavy, too complicated, and most importantly, it consumed too much electrical power. Car companies in Germany and Detroit looked at this future and walked away from it. Instead of pursuing revolution, they chose incremental improvement. They believed the internal combustion engine and low-voltage electrical systems would dominate forever. They were wrong, because they failed to anticipate the rise of high-voltage electric vehicle platforms. Electric cars now provide massive energy reserves, the exact resource needed to finally power truly active suspension systems. And that leads us to the technological turning point we are seeing today. BYD, a company that originally built mobile phone batteries in Shenzhen, has essentially picked up the technological torch that Western companies abandoned. With vehicles like the Yangwang U7 and its revolutionary DSUS system, BYD has brought linear motor suspension into mass production. But we need to be precise about what this technology actually is. It is not air suspension. Air suspension simply replaces a steel spring with an inflatable rubber chamber. It still depends on slow gas compression. The DSUS system eliminates both fluid and gas entirely. It is a fully dry system. At each corner of the car sits a powerful three-phase electromagnetic linear motor. Imagine the propulsion system of a high-speed maglev train compressed into a small cylinder inside the wheel arch. Instead of building hydraulic pressure, electrical current generates force directly. And it does this almost instantly. The number that defines this revolution is 10 milliseconds. That is the reaction time of the system. For context, the human brain needs roughly 200 to 250 milliseconds to recognize a visual threat. A blink of an eye takes about 100 milliseconds. The DSUS suspension reads the road with LiDAR and sensors, calculates the required force, and moves the wheel 20 times faster than you can even perceive the bump. This makes something called sky-hook suspension theory possible in the real world. The vehicle body remains almost perfectly stable relative to the horizon, while the wheels move rapidly beneath it. The wheels extend into potholes and retract again before the shock even reaches the cabin. To passengers, it feels like the road itself has been smoothed out. Critics once argued that heavy electric motors near the wheels would ruin handling because of increased unsprung mass. That concern applies to passive systems, but the DSUS system is active. The motors are powerful enough to control their own mass. They can push the wheel downward faster than gravity itself, exceeding 9.81 meters per second squared, forcing the tire into the road surface. The suspension is no longer just absorbing shocks, it is actively generating grip. Now consider the extreme example, the Yangwang U9. This car uses the even more powerful DSUS X system, the most advanced version of the technology. Here we see the full potential of modern 800-volt silicon carbide electric architectures. The suspension system alone can deliver 36 kilowatts of peak power. That's more power than the entire drivetrain of many small city cars. Why so much power? Because overcoming gravity requires brute force. The viral videos showing the U9 jumping off the ground are not marketing gimmicks. They demonstrate the sheer power density of the suspension motors. For a 2.5-ton vehicle to launch itself upward, those motors must deliver explosive force instantly. But the real breakthrough is safety. The U9 can actually drive on 3 wheels. In traditional supercars like a Ferrari, McLaren, or Lamborghini, losing a wheel at high speed would cause catastrophic loss of control. The chassis collapses, the asphalt scrapes the car, and the car often spins violently. The U9 handles this differently. Its sensors detect the loss of load instantly. The system retracts the damaged corner, lifts it clear of the ground, stiffens the opposite side, and uses torque vectoring to keep the car stable. A catastrophic failure becomes a controllable situation. The system adds a new level of redundancy to vehicle safety. When you compare this to European competitors, the difference becomes obvious. The Porsche Panamera uses a 48-volt active anti-roll system. It works well, twisting a stabilizer bar to reduce body roll. But it cannot lift the car, it cannot jump, and it cannot drive on 3 wheels. Against an 800-volt active suspension system, that technology suddenly looks outdated. The third piece of this ecosystem is the Yangwang U8. This vehicle uses the DSUS P hydraulic suspension system. Unlike the Z and X systems that prioritize speed, the P system focuses on massive strength and travel distance. It rivals the best off-road machines from brands like Land Rover and Toyota, and in many ways surpasses them. The system can stiffen the body by 200% during highway driving to eliminate body roll. Off-road, it unlocks up to 155 millimeters of wheel articulation. Even more impressive, the vehicle has an emergency flotation mode. If the SUV enters deep water, it seals its body, raises the suspension, and uses its spinning wheels to slowly propel itself like a boat. The car can even perform a tank turn, rotating in place while the suspension stabilizes the chassis. If you get a flat tire in the desert, the suspension can lift the damaged wheel high enough for you to replace it without using a jack. The car literally lifts its own corner. There's also a fascinating thermodynamic advantage. Traditional suspension wastes energy. When a car hits bumps, the dampers convert kinetic energy into heat. That energy disappears into the air. But electromagnetic suspension works differently. The motion of magnets through coils generates electricity. This means the suspension can actually harvest energy from road vibrations. On rough roads, it sends small amounts of electricity back into the battery. This concept is called regenerative damping. It won't fully recharge the battery, but it offsets the power consumption of the system. The rougher the road, the more energy the suspension recovers. There's also a fascinating thermocultural advantage. For decades, car brands like Lotus Cars, BMW M, and Porsche relied on legendary engineers to tune suspension components. They experimented endlessly with springs, bushings, and dampers to find the perfect balance. It was almost an art form. But software-controlled suspension changes everything. The driving feel of the car is now determined by code. Stiffness, rebound speed, body roll, all adjustable through software. The car's personality can be updated over the air.